I'll be reading out of issue number 42, which is published in July 1988. The title of the article is XT Theory of Operation, Putting All Those Smart Chips Together. In the little blurb at the beginning of the article that this editor often likes to add, he says that Larry's been researching and writing the pieces on the XT's LSI chips. So that's the processor, timer, DMA controller, etc. So it was natural that he take the lead in this final piece. This is the theory of operation, the how all those fancy ICs work together as a computer. We're also finishing up one of our famous wall-sized schematics for the XT. If you have a hankering to really see what we're talking about, then check the end of the article for details. So yes, this article was written by Larry Fogg, mostly, and then David Thompson. Okay folks, here it is, pretty nearly the whole circuit in one place. We're using device names S0474S04 in place of U numbers, and we're using signal names, for example reset, in place of pin numbers. We're doing this mostly because most of you have clones, and though the U numbers and pin numbers may differ, the device names and the signals remain. Note, a signal named reset would be active, would reset the system, when the line is high, so that's 4 volts or above. A signal named reset, sometimes called reset not, or reset bar, would be active when the line is low, that is 1 volts or lower. Schematic drafters usually put a line above names of signals that are active low. Okay, the first section is titled Clock. The PC's heartbeat comes from an 8284 clock generator. All of the 8000 series chips here are spawn of Intel. Actually, the 8284 spits out 3 clock signals. OSC, a 14.31818 megahertz symmetric square wave, goes to the I/O bus for use by peripheral cards. This signal is also used by the 8284 to create the other 2 clock signals. The frequency of the OSC output depends on the crystal connected to the 8284. A variable capacitor labeled Color Adjust by IBM lets you fine-tune the crystal's frequency. The name Color Adjust comes from the fact that IBM's CGA card requires a very precise 14.31818 MHz and a 3.579 MHz. So this last number is what you get when you divide the first number by 4. The 8284 can also accept an external clock input and switch between that and OSC, but its clock source select input is held low through an LS04 inverter connected to plus 5 volts. This assures that OSC will always be selected, a good thing since the external clock input connects to thin air. But why not just tie the select line to ground? Dave guesses the unnecessary inverter is a vestige from the XT's development days when IBM may have toyed with a 2-speed system. Larry thinks it's sheer perversity. Clock 88 provides the 4.77 MHz, 33% duty cycle signal, which serves as the main system clock. The third output, a peripheral clock called PCLK, gives the 8253 timer chip and the keyboard section a symmetric reference signal. In true blue XTs, the 8284's RES input connects to a PWRGOOD signal. So you see how that says power good, right? So connects to that signal from the power supply. A loss of power causes a reset. None of the clones we've looked at implement this feature, but you can create your own reset switch by shorting the reset input to ground. This initiates a high on the 8284's reset output, which connects directly to the processor and any coprocessor. The falling edge of this reset triggers the reset sequence. During direct memory access, DMA transfers, some rather convoluted logic circuitry sets up the first of 2 possible ready inputs to the 8284. With this input held low by the DMA wait signal, the 8284's ready output goes low. When the 8088 sees this low, it inserts wait states until the DMA controller finishes its transfer. Ready can also be forced low by slow devices on the I/O bus. Alright, the next section is very small. It's titled Processor. So much for the heart, on to the brains. We'll talk about most of the 8088's function when we deal with the peripheral chips, but one thing should be mentioned here. The 8088 can be configured in two modes. In the XT, the mode select input MNMX, which stands for min and max, connects to the ground. This selects the maximum mode where the 8088 receives help generating bus control signals and can deal with coprocessors. Next section is titled The Buses in the Bus Controller. The 8088 can handle 8 bits of data and 20 bits of address. It needs only 20 pins for both data and address because it uses 8 pins for double duty. So the 8 bits of data share the 8 least significant address lines. Separating the data from the address takes place as follows. And a quick side note here, I was just watching a video about how the new Intel server chip has 7,500 pins, or some number slightly higher than 7,500. That's pretty mind-blowing in the context of this 1988 article. During the first part of the bus cycle, the 8088 places a complete address on its AD0 through AD7 and A8 through A19 pins. Okay, so we got a signal on those pins. It also sends information to the 8288 bus controller via status lines S0 through S2. The 8288 decodes this status information and generates an address latch enable. By the pint, of course, he says. And anyone needing help visualize this, I'd recommend Ben Eater's YouTube channel. So ALE, address latch enable, latches most of the address into two LS373s. So that's plural. And LS244 buffers the remaining 4 bits, which is A8 through A11. Address enable board enables outputs for all 3 chips. Once the address has been latched, we deal with data. New status outputs from the 8088 till the 8288 to generate a data transmit receive signal. So that's abbreviated as DT-R. These signals control the direction of data flowing through an LS245 octal bus transceiver connected to pins AD0 through AD7. So we have data and we know whether the processor will be receiving or sending. Another tweak of the status lines makes the 8288 pump out one of 4 sources and destinations: I/O read, I/O write, memory read, or memory write. Okay, that should look like a nicer format. Okay, so if you're taking notes, you can pause right here. Finally, through its status lines, the 8288, the 8088 sends a data enable, abbreviated DEN. So no, that's not Denver, it's data enable. So through these status lines and the 8288, the 8088 sends a data enable to the LS245, and we've placed address and data on the address and data buses. That takes care of one set of address and data signals, the ones belonging to the internal buses. These buses talk to the processor's RAM addressing logic, RAM data, and most of the I/O bus. So it looks like that's J1 through J7. J8, the rightmost expansion slot, is the black sheep of the family. More on J8 later. External address and data. The demultiplexing circuitry described earlier doesn't have enough oomph to talk to everything on the address, data, or control buses. Every input on an address line, for instance, adds a little capacitance and a little current drain to the line. So in order to give these little demuxers a break, the buses are divided into 2 parts, internal and external. The demultiplexers drive the internal address and data buses. Buffers then transfer the internal signals to the external buses. The external address bus, for instance, services the system RAM, system ROM, I/O ports, and the expansion slot J8. 3 LS244s buffer the addresses into, or onto, I should say, the external bus. 2 of the LS244s, carrying A8 through A19, have their 2 active low output control pins tied to ground. So part of the external address bus, XA8 through XA19, always reflects exactly the contents of the internal bus. The LS244, responsible for A0 through A7, has its output control pins tied to AEN BRD, so you can see that is AEN board, address enable board, I assume. That's fine, but why treat A0 through A7 differently than A12 through A19? Both groups of addresses originate in L3 or LS373s, controlled by identical inputs. If anyone out there was involved in the design of the XT, or knows someone who is involved in the design, we'd sure like to talk to you. Some of the workings of this machine aren't immediately obvious. The external data bus is a bit stickier. Addresses go only one way, from the processor, or DMA, to memory, or I/O. Data has to travel in both directions. An LS245 octobus transceiver handles the bidirectional buffering. The LS245's direction control input, DIR, connects to an LS27 positive NOR gate, which has 3 inputs. When any of the 3 inputs go high, the output of the NOR gate goes low. That forces the LS245 to pass data from the external data bus to the internal data bus. So at this point, I'm going to end the video. Maybe I'll pick this article back up. It is interesting, but extremely technical. On the next page is a huge diagram of the XT processor circuit. So very interesting, right? You get to see all the pins that Larry Fogg is talking about. And then on the page after that is the XT RAM circuit. And yeah, for this one, I think I'll only come back to reading it if there's demand. So let me know in the comments if you wanted me to keep going. Else, I'll just send my reading of the XT internals. I'll just leave it at this. Thanks for watching.